This is part 3 of color perception. I did end up adding some color to this, as these used to be white slides, and it's funny, throughout my early days of teaching I would always be wearing, by accident, black, khaki, and grays, and these like really non-color wardrobes, and I noticed that my slides are white, so I stole this. I think this is called Firestarter. It's in the notes. I took it from the internet. If you want to buy the lithograph, it is $600, but this is by expressionist artist Lamar Briggs, and I did just steal it off the internet. I tried to give some credit there, but that's as good as it gets. So the first function of color vision that I usually go through is just the beauty that color gives us. Every once in a while, we have a really great exhibit at the Columbia Museum of Art that I can refer to. And one time I remember teaching this class, and it was Mark Rothko, who basically just uses colors in this really expressionistic fashion, similar to the Joseph Albers that we saw at the very, very beginning of discussing color perception. But I also have up here, so these are things I stole from the internet. One is a picture of the fall in New England, and the other is a Monet painting of the spring in France. And I feel very lucky that I get to teach this class, and that color vision usually comes at some point during the fall when I can see the change in colors and it makes sense to talk about them, or at some point during the spring when, again, just the blooming of the flowers and the differences in the colors that are available to us are there in the spring are really incredibly beautiful. And so it's not a bad idea, again, to pause. I'm going to keep suggesting that you pause things in the next couple of slides, like next few presentations, to really appreciate how much beauty color gives us, to look out your window. Like, I live in the woods, and everywhere I look, there are different shades of green and brown, but it's the complexity of the greens and browns that are really beautiful when you're off in the pine tree woods of the Carolinas. Another function of color vision is that it signals identification and classification. So it helps us to identify objects and classify objects. This is true for both man-made objects and objects from nature. And so these pictures are from stimuli from Tanaka and Presnell in 1999, where they presented participants with either, I'm just going to use the bananas that are their canonical kind of yellow color, maybe with a little bit of green-brown, versus bananas that were this purple color. And people just had to identify what the object was, and they were faster to identify the bananas when they were of their canonical kind of yellow color. And that makes sense when we think through it, that the color of an object helps us to identify that object. Color also helps us to identify food sources in comparison to what's around those food sources. So this is helpful for our survival. This is actually what is commented on maybe very quickly in the article about the genes of color vision, where he talks about, I'm pretty sure it's in that article, he talks about how New World monkeys, monkeys used to have dichromatic color vision, and New World monkeys had this mutation, and they kept this third cone around because it helped them to distinguish their food specifically. And so how exactly that mutation occurred and what it gave to the monkeys, it sounds like it depended on their particular food source. So for a particular New World monkey that ate bamboo, the ripe, fresh bamboo was differentiated from its surroundings based on what those cones gave that monkey the ability to distinguish. Hope I got my words in the right order there. And so this picture is basically showing trichromatic color vision, somebody who might be going to pick berries. I can't tell if these are raspberries or red blackberries that aren't black yet, but if you've ever picked blackberries specifically, I've not picked raspberries very often, but blackberries have stickers and thorns around them. And if you're monochromatic, if we look over to the right-hand side there in B, a person who is monochromatic is not getting the differentiation in the color, so that they would have to feel around and prick their hands in order to find the berries by feel. And what color vision gives us is the ability to see those fruits and berries. And so that was a real leg up, an advantage for us in the evolutionary chain. This is usually another place where we take some pause and people share their experiences with color vision. And again, this is typically done a little bit earlier, and I think it's important for us to share perspectives on color vision. And I've done a little bit from my own perspective of not really seeing the distinction of colors that I think a lot of people see, not matching my clothes. I mean, I think I see the distinctions of color. I'm just not really aware of how they go together, how they match all that well. I do really enjoy the fall and the spring, and I enjoy the differences in greens. Usually when I go into depth perception, which we're not going to get to go into this semester, I talk a little bit about motion parallax and some of the two-dimensional cues to depth perception. And I usually do this whole, when I'm driving home, I am in the painting. Okay, I am in the video game. When you're driving and moving through something, the motion and the depth and all of that is the motion parallax. All of that is changing so fast, and what's closer to you is changing more quickly than what's far away. So clouds are not, or they're moving very slowly in comparison to the trees that are right next to you or the guardrails or whatever. And if you add kind of color to that, I do this almost every day that I drive back and forth from school, of this kind of just appreciation and awe that I am in the painting. It is happening, or the video game. It is happening around me in real life, in real 3 dimensions, in real motion, and my brain is doing all that calculation and all those different neurons are firing in different patterns very quickly in order for me to take in all that information, and it kind of blows my mind. And so if I could get you to, even since we're not going to talk about motion and depth and all that, even just to experience and think about how awe-inspiring color is. Usually I have students share at this point, and it's helpful, I think. I've had students talk in those discussions about their experiences of warm and cold, when they talked about synesthesia and so forth. Again, I don't feel those very strongly, and but I think it's really interesting for us to share with each other and think about how other people are experiencing color, why we have different favorite colors, how much of that is classical conditioning versus how much is something different. I don't know. It's a fascinating aspect of our perceptual worlds. I am going to share Mr. I's story. It's on page 195 of the Goldstein book. He talks about a man who was an artist, and he had a car wreck. I think it was a car wreck where he got some brain damage, and he ended out with the cerebral achromatopsia. So if you read the cerebral achromatopsia article, you'll see how complicated that can be, and what region of his brain was damaged. It looks like part of V4, but I'm not going to say that for sure because I don't know if he had some prosopagnosia or other issues. But clearly, partly because he was an artist, I think, this change from his world of being a trichromat and seeing the range of colors that we see to becoming a monochromat and seeing no real difference in color, only really differences in maybe wavelength and shades of gray, he finds it depressing and disturbing for a while. He talks about not really seeing his dog very well because his dog's just another shade of gray against the trees and the grass and everything. He talks about sunsets no longer being fascinating or interesting or fun, and then maybe the color of some kind of food that he eats, that it's just not even enjoyable to eat food because of the tomato is no longer red, the orange juice is no longer orange, it's just this blah kind of brownie gray color that has no real feeling for him anymore. He does become an artist that deals solely in blacks and whites and shades of gray. He eventually gets over some of this depression that was really caused by his loss of color vision, but you can imagine how hard that must be, and especially given his background. And again, we all experience colors to a really different degree, and how much they affect us is really to a different degree. It's all really fascinating. So that brings us nicely to talking about color in the cortex and this kind of acquired color deficit, because usually what happens, usually the color deficiency that we have because of defects or absences of cones, we are born with those deficiencies. But typically the way an achromatopsia occurs is we have some kind of brain damage. And a lot of times this is brain damage due to stroke. But again, Mr. I had a car wreck, so it depends on how the brain damage occurs. Cerebral achromatopsia, A meaning not, right? So a world without color or not having color is a monochromatic world due to damage in the cortex. So, and remember, the cortex, the cerebral cortex, is that outer layering of the brain. So more easily damaged than by trauma than subcortical structures. These people appear to still have some experience with wavelength, but not in the form of color perception. And the question is here, is it really more enhanced sense of differences in gray? What do we know about color in the cortex? I actually had my brain and behavior class this year read a different cerebral achromatopsia article where they were trying to figure out exactly what's damaged and what is V4 and V4 alpha and what does this mean for our perception of color. Well, the overall answer is we don't know much. I mean, we know some things, but they don't add together into some nice, clear answers. We know that there's no single module for color vision, that we are seeing cells that are responding to color all the way from those retinal ganglion cells through the lateral geniculate nucleus to V1 to V4, and they help us with, they go into the inferior temporal cortex to help us understand what objects are, but there's not a single module for color vision. We know that some cortical neurons are responding to just certain wavelengths. I actually had a great conversation in my honors class where the person was talking about P cells, M cells, and K cells, where those K cells are responding to shorter wavelengths, and the P cells, it looks like not so much, which is going to influence subcortical neurons and cortical neurons and what they are responding to. In many areas of the cortex, including V1 and the ventral stream, so where we are doing our object recognition, we have some neurons that have opponent processes. So we saw this in the last bunch of slides of the red, green, blue, yellow opponent processes. Those continue through the cortex. And we know that neurons that respond to color also respond to form and orientation. As we are going into that what pathway and figuring out what objects are, color helps us with that. I often also, at some point in all of this, usually have somebody else who is extremely myopic in my classes and mention something like, and if you are extremely myopic and the world is completely blurry when you take off your glasses, raise your hand if you know how much you use your color vision. So red lights and green lights really stand out to me. What I see with the McDonald's sign is just yellow and red. And it lets me know that that's a McDonald's sign, even though I cannot see the giant M. Okay, those colors help us to understand what objects are. What do we know about color in the cortex? We know that it is very distributed processing. So this is a study that was done in 2010 where they asked participants whether or not two blobs were the same or different depending on texture, You can really see it in the first one, but the texture is different. Color or shape. Okay, and what we can see in the brain imaging there is the activity in response to texture. We see that back in the back of the occipital lobe. Color, we see the green kind of already, just the green, when I'm just responding to color, is kind of distributed up there. The red must be going into the inferotemporal cortex when we were dealing with shape. The yellow, okay, what the yellow is responding to all three, or color and anything else. And so you can really see, if you put the green and the yellow together, you can really see how distributed color processing is. And so I asked the question here, this is one of those questions I don't expect a student to have an answer to, is how does cortical damage cause achromatopsia? Because, right, if it's really distributed, then how can a specific brain damage cause a loss of color? Well, if you read the article on achromatopsia, which was just one of the choices, it's complicated. And what aspects of color vision those people are losing, even that's complicated. Is it memory for colors? Is it memory for colors of specific objects that I'm used to seeing in a particular color? Is it color constancy? Is it color but not wavelength? It's all really very complicated, and it's very distributed, and rarely is it a situation where we've lost all of that stuff. And if we've lost all of that stuff, we've usually lost other aspects of the inferotemporal, that pathway. And we've lost some of our, usually it's prosopagnosia, and we've lost our facial recognition in addition to the processing of color. And so some of that subcortical and V1 kind of processing of color is still occurring, is just not getting up into the kind of conscious perception of color, if that makes sense. So some questions that we might ask ourselves at this point as to differentiate some of this is, where is information about wavelength processed? Because I'm going to talk about MS here, who has damage to the cortex, has cerebral achromatopsia, but the photoreceptors are still intact, and MS can still use wavelength information. He appears to be able to detect the line separating two adjacent fields of different colors of different wavelengths, and that's why I have on a previous slide that kind of in brackets this are they differentiated? Is it more sensitivity to differences in gray? Because it's still going to be harder to pick blackberries and do that kind of stuff, but wavelength information can be maintained when we lose our ability to see color. And then a separate question then is where is the perception of color, the actual experience of color, determined?